Nearly 11 kilometers beneath the Pacific Ocean lies a place that should not allow life to exist. At that depth, pressure is more than 1,000 times higher than at the surface, strong enough to distort proteins, collapse cell membranes, and tear apart the chemistry that keeps cells alive. The temperature hovers near freezing. Chemical reactions slow to a crawl. Metabolism should fail. There is no sunlight, no photosynthesis, no energy source to support a food chain. By every biological rule, this place should be sterile. It isn't. In 1960, two men descended into this abyss, expecting confirmation of impossibility. What they found forced biology to reconsider its limits. Today, we're going back to Earth's deepest point to ask a more unsettling question. If life survives here, what exactly are the limits? The year is 1875. The British ship HMS Challenger has been mapping the ocean floor for 4 years. Brutal work. They lowered a lead weight on a rope until it touched the bottom, then hauled up meter after meter of cold, heavy line. At the time, the rules seemed settled. The deep ocean was uniform and predictable. A flat seabed of mud and silt, typically 3 to 4 kilometers down. Month after month, the measurements are boringly consistent. The seabed remains at 3 to 4 kilometers down. Flat, muddy, nothing special. Then one day, alone in an empty ocean 2,000 kilometers east of the Philippines, something strange happens. That assumption was about to shatter. The crew was taking what they assumed would be another routine measurement. The weight drops past 3 kilometers, then 4, then 5. It keeps going. By every previous measurement, the bottom should already have been there. The crew ties on more rope, still descending. What had seemed like a featureless plane was revealing itself as something far more extreme. We can only imagine what went through their minds as they added line after line, that weight continuing its journey into the darkness directly beneath their wooden hull. They were undoubtedly terrified. The ocean floor was not stable and uniform. It was fractured, dramatic, and far deeper than anyone had predicted. Eventually, the weight struck bottom. More than 8 kilometers down, they discovered the Mariana Trench. The rule of a shallow, monotonous seabed had been replaced by a new reality. If they'd sailed just a bit further west, they would have found something even more extreme. The Challenger Deep. 11 kilometers to the bottom. Drop Mount Everest in this hole and it would vanish completely. The peak would sit 2 kilometers below the surface. That's how deep this place is. The ocean, once thought to be flat and unremarkable at depth, concealed the deepest place on Earth. The Pacific plate beneath the Mariana Trench is 170 million years old. Heavy, dense, on its way back into the mantle. At the western edge of the Pacific, it collides with the younger Philippine plate and sinks beneath it. This process is called subduction. The trench forms when one plate bends under the other. The forces are violent. They generate earthquakes, volcanoes, and some of the most extreme geological environments on Earth. Nearby, carbon dioxide exists as a liquid, not a gas. Pressure rewrites its chemistry. There are pools of molten sulfur. Hydrothermal vents blast superheated mineral-rich water into the ocean. Environment scientists believe may resemble the birthplace of life itself. And this instability is what carved the deepest place on Earth. For life to exist at the bottom of the Mariana Trench breaks 3 fundamental rules. Rule 1, pressure. At 11 kilometers down, the pressure is like a 1-ton weight on your thumbnail. This pressure should cause proteins to unfold, cell membranes to collapse, and DNA to become unstable. Nothing should function. Rule 2, temperature. The water here hovers just above freezing. Metabolic processes should be too slow to a crawl. Chemical reactions that power life should stop. Rule 3, energy. Life needs energy. On the surface, that energy comes from the sun through photosynthesis. Down here, there is no sun. No sun means no photosynthesis, no base of the food chain, which leaves nothing to eat. By every scientific model, the Mariana Trench should be completely sterile. It's not. We're going deeper, into the trench itself, thousands of meters below even these volcanic wonders. Down into the Challenger Deep for the most extreme dive possible on Earth. At 10,935 meters, you might think the Mariana Trench is somehow a freak occurrence, an unexpected deep hole of unusual depth. It's not. Other Pacific trenches reach similar depths. The nearby Tonga Trench, 10,800 meters. The Philippine Trench, 10,540 meters. These rifts in Earth's crust constantly change. The depression causing the Challenger Deep is temporary. One day it will be dragged into the magma, and somewhere else will become the deepest point on the planet. Exploring such depths presents enormous challenges. The number one challenge is pressure. Swimming to the bottom of a pool, you feel water pressure in your ears. At just 3 or 4 meters, it becomes uncomfortable. At Challenger Deep, the pressure is unimaginable. More than 1,000 times the surface pressure, equivalent to a 1-ton weight on your thumbnail. That pressure destroys most living cells. But it's not just living things that get crushed. The destructive power is astonishing. Even equipment designed for extreme depths can fail catastrophically. Military submarines that secretly patrol our oceans can only dive safely to around 1,500 meters. To reach the Mariana Trench bottom, you need serious equipment. In 1960, 2 men decided to find out what was down there. Don Walsh, a US Navy lieutenant, and Jacques Piccard, a Swiss scientist. Their vehicle was called Trieste, basically a thick steel sphere hanging under a giant gasoline-filled tank. The sphere could barely fit 2 people sitting. The walls were over 12 centimeters of forged steel, and the windows were tiny blocks of plexiglass. The descent took nearly 5 hours, and it came with serious conditions. There was no communication with the surface, and no rescue plan if something went wrong. All they had was hope that the mission would not fail. At around 9 kilometers in depth, there was an enormous bang, but they continued. They didn't realize that one of the thick outer plexiglass windows had cracked. One of the key components preventing their capsule from imploding and being crushed like an aluminum can. They were at the absolute limit of what Trieste could handle, and they went 3 kilometers deeper. Their view consisted of 2 tiny viewing ports, just 50 millimeters in diameter, illuminating a small area in pitch blackness. When they finally reached the bottom, their arrival had kicked up clouds of sediment. For several minutes, they couldn't see anything through their tiny windows, just their lights reflecting off particles in the water. Then, the sediment settled, and they saw something moving. They saw life. They reported seeing a flat fish. Something was swimming across the bottom. Scientists now think it was probably a sea cucumber, but that's almost besides the point. There was life at the deepest point on Earth. They remained there for 20 minutes, suspended above a seafloor once thought to be barren. The descent was so dangerous that no one would attempt it again for half a century. Think about that. During those 50 years, nearly 7,000 people climbed Mount Everest, 12 people walked on the moon, but only 2 had been to Challenger Deep. The next manned ascent didn't occur until 2012, when James Cameron made the first solo dive into the Challenger Deep aboard the Deep Sea Challenger. Since then, there have been roughly 20 more dives into Challenger Deep. The number of people making this journey has finally exceeded the number of people who've traveled to the moon. In 2021, Hamish Harding made the longest and deepest dive into Challenger Deep. 2 years later, he was among 5 people killed when the Titan submersible imploded on a mission to explore the Titanic wreck at only 3,800 meters. The ocean does not forgive mistakes. Let's make the journey ourselves. At the surface, there's nothing but the empty Pacific Ocean. No land visible in any direction. We drop beneath the surface. The world above disappears fast. At first, the ocean feels alive. Warm water, sunlight, motion. Then the light thins out. Photosynthesis collapses. The food chain becomes a trickle. And the deeper you go, the rules start failing one by one. We're 1 kilometer down. The last traces of sunlight vanish. From here on, the ocean is permanent night. Creatures begin to look unfamiliar. Some evolve enormous eyes to capture the faintest glow. Others abandon vision entirely and rely on pressure and vibration. Bioluminescence flickers in the dark. Signals, lures, traps. Predators use light as bait. Prey use it as camouflage. Food is rare. Energy is scarce. And scarcity pushes bodies into extremes. This is deep-sea gigantism. In a world where meals are unpredictable, being large becomes an advantage. You survive longer between feedings, you're harder to kill. Size becomes survival strategy. But even here, this is not the bottom. We are still thousands of meters above the most extreme environment on Earth. We've left the Midnight Zone behind. We're now in the Hadal Zone, named after Hades, the god of the underworld. Life here exists in darkness, under near freezing temperatures, and the pressure is now beyond anything most life can tolerate. Cold water flows through these trenches from Antarctica, part of a global current system that affects weather worldwide. To life forms adapted to these depths, this constant supply of cold, pressurized water is vital, enabling them to access more oxygen in an environment where every small advantage determines survival. According to every prediction, these depths should make life impossible. The immense pressure disrupts the structure of proteins, the cold slows metabolism toward collapse, and the darkness removes any reliable source of energy. And yet, life is not merely present here, it flourishes, forming a diverse ecosystem of species found nowhere else on Earth. Even the shallow parts of the Mariana Trench are 8 kilometers deep. The seafloor is covered in fine silt that puffs up with any movement. There's more life here than in the open water above. Our lights illuminate mats of bacterial ooze on rocks rising above the silt. These bacteria aren't using sunlight for energy. They're using chemicals from volcanic vents, hydrogen sulfide mostly. They turn this into energy through chemosynthesis instead of photosynthesis. It's nowhere near as efficient, but when you're 8 kilometers from the sun, you use what you've got. And here's where it gets interesting. Just as these microbes create life from rocks in this dark, these bacteria become food for other things. The cycle of life begins even at these depths. The only other food supply is scarce organic matter floating down from above. But after falling through 8 kilometers of water, passing marine life constantly scavenging for any food, very little makes it this far. The main scavengers at this depth are giant amphipods. Don't get too excited by the use of the word giant. Growing to more than 30 centimeters, they're giants compared to other amphipods, normally only a few millimeters long. There are also sea pigs, strange translucent creatures that are actually a type of sea cucumber. They crawl across the bottom on leg-like projections, searching for anything edible. When a large creature dies and sinks to this depth, a whale carcass for example, these scavengers organisms not only survive, but they're also specifically adapted to require this pressure. Remove them from these depths, and they die. Not from decompression, from the absence of pressure. Here we encounter what looks like a large lump of jelly protruding from rocks, xenophytophores, single-celled organisms growing to 20 centimeters or more, about the size of a football. That is insane for a single cell. Impossible, yet here they are, made possible by an environment that would destroy surface cells. Normal cells have hard size limits. Nutrients and waste move in and out via diffusion, a process that only works across short distances. A cell 20 centimeters wide should starve at its core. But xenophytophores evolve membrane compositions and protein structures that only function under extreme pressure. Bring one to the surface, and it doesn't decompress and die, it dies from the absence of pressure. It requires these conditions. The environment we assumed made life impossible is the very thing that makes this life possible. And that is the real mystery of the Mariana Trench. It is not simply that life exists at these depths, but that the organisms here are so precisely adapted to this environment that they depend on the very pressure, cold, and darkness that would destroy most other forms of life. Examples of life pushed to extreme limits, like the xenophytophores, teach us how cells work, how processes inside cells and bodies can be adapted and changed, and this is where we learn about life itself. New medical treatments and cures frequently originate from studying life's oddities on our planet. At these depths, most life we find is distinctly odd. Even here, sediments hide bristleworms and decapods like shrimp that burrow through settlement, surviving on meager organic particles descending from the surface. Above the silt, we may see copepods, free-swimming crustaceans, or sea cucumbers. But as we descend deeper from the surface, life becomes scarcer for one good reason. The deeper we go, the less is available to support life. As we leave this higher trench floor level and descend a further 3 kilometers into Earth's deepest waters, this effect becomes even more pronounced. But one common assumption was that this water is too deep for any fish, or at least that's what's currently believed, but we simply don't know. There has been so little meaningful exploration that claiming to know much about what exists in our ocean's very deepest parts would be dishonest. What lives there? Honestly, we don't really know. At the time of this video recording, 27 people have visited Challenger Deep, but most of these visits were brief. Some were brief missions with limited scientific scope. Others involved lowering a dead fish in front of a camera to see what showed up. What appeared were amphipods and sea cucumbers, but that doesn't mean that's all that's here. It just means that those things are attracted to dead fish on cameras. If anything, this raises the question, what are we not seeing? Imagine trying to understand the Grand Canyon by dropping a camera into one spot a few times a night. Maybe you catch a spider and some ants on film. Would that tell you everything about living in the Grand Canyon? Of course not. But that's a realistic comparison of how we've explored the deepest oceans, an area almost 700 times larger than the Grand Canyon itself. Our deep oceans are extremely difficult to explore. They're remote, covering vast areas. Equipment needed to research waters on the seafloor must withstand exceptional conditions. But let me put this in perspective. We've sent people to the moon. We've sent vehicles to explore Mars, Saturn, and even Neptune at our solar system's edge. Why do we still know so little about an area covering more than half of our own planet? Our deep oceans are remote. They cover vast areas. The equipment needed to reach these depths has to withstand conditions that would destroy almost anything we can build. Medical breakthroughs often come from studying life in extreme environments. Organisms that survive in boiling volcanic vents have given us heat-stable enzymes used in DNA testing. Who knows what we could learn from creatures surviving at Challenger Deep? But there is a deeper implication to all of this. If life can survive under crushing pressure, near freezing temperatures, and permanent darkness at the bottom of our own ocean, then the boundaries we once placed on habitability begin to fall apart. The subsurface oceans of Europa and Enceladus no longer seem so unreachable in biological terms. And beyond them, there may be countless worlds with liquid water hidden beneath ice, waiting under conditions that no longer feel impossible. The creatures of the Mariana Trench may offer our first real glimpse of what life beyond Earth could resemble. Not intelligent beings stepping out of spacecraft, but organisms shaped by extremes we once believed were incompatible with biology itself, expanding our definition of what life can be. If evolution can carve thriving ecosystems out of crushing pressure and perpetual darkness here on Earth, it becomes much harder to argue that our planet is the only place where life has taken hold. Do you think life exists somewhere else in the universe? Or is Earth an extraordinary exception? I would love to hear your thoughts down in the comments below. The most important lesson from the Mariana Trench is this: every time we think we understand life's limits, life proves us wrong. For over a century, scientists were certain nothing could survive at the bottom of the ocean. The pressure, the cold, the darkness, to them it was simply impossible. They were completely wrong. What else are we wrong about? What other impossibilities are just us not understanding how adaptable life actually is? The Mariana Trench keeps its secrets well. 11 kilometers of water form a barrier few have ever crossed. In the rare moments we have reached the seafloor, we have glimpsed creatures that defy expectation, relying on biological mechanisms we are only beginning to understand, surviving in conditions that continue to challenge our explanations. Now, here is what we do know. Life at these depths challenges biological limits we once believed were absolute. A single cell the size of Xenophile 4 should not remain stable under such pressure. Proteins should lose their functional shape. Metabolic systems should slow beyond viability in temperatures this cold. And yet, they persist. What remains hidden in the darkest reaches of our oceans? Each organism discovered at Challenger Deep raises deeper questions. If life can adapt to these extremes, then our definition of biological possibility is incomplete. If a single cell can grow to the size of a football under crushing pressure, what other principles we consider fixed are only assumptions shaped by limited exploration? The Mariana Trench is more than the deepest place on Earth. It is a natural laboratory at the edge of survivability, and we have barely begun to study it. As exploration advances and access improves, future discoveries may force us to reconsider the boundaries written into our textbooks. Because in that immense darkness, beneath 11 kilometers of ocean, life did not retreat. It adapted, it specialized, it flourished in a world that should have excluded it. The organisms of the Mariana Trench do not merely endure extreme conditions, they are defined by them. What we once thought were hard biological limits may instead be reflections of how little we have seen. And if life can transform impossibility into habitat here, what else might be waiting beyond the edges of our exploration? If this changed how you think about life's limits, subscribe so you don't miss out on our next exploration.